So now what we are going to do is, given a max heap, okay, so we started with the original array and now we have max heap version of the array. So we went through the max heap building process. So now given a max heap and the corresponding array, we have to go through the second stage of getting the array sorted. Alright, so now what we are going to do is this. Again, we're going to go through a sequence of iterations. And in each iteration what we are going to do is this: move the data at the root node to the last accessible node of the array. Now to begin with, the entire array is accessible, right? So the index is 0 to 9, which is 0 to n minus 1 if you look at a code. So we are going to move the element at the root node at index 0 to the last accessible portion of the array, which is index 9. So 10, which is the root node, goes to index 9, and then basically you're swapping. So 10 goes to this position and 3 becomes the root. Okay. So the data at index 9 is moved to the data at index 0, and the data at index 0 is moved to the data at index 9. So 10 comes down here and 3 becomes the data of the root node. Now once we do that, this is the first iteration, we say that is iteration 0. The 10, you see this is a max heap. So in a max heap, the root is always the maximum of the elements in the heap. So if you see here, 10 is the maximum of all the elements in the heap. So the node at a level is the maximum of all the nodes further down. So similarly, you see here 8 is the maximum of everything starting from here. So 8 is larger than 7 and 6, then 1, 4, 3. 9 is larger than 5 and this 5. 7 is larger than 1, 4. 6 larger than 3. So that's the property of a heap or max heap or min heap. So in the case of a max heap, if the node at a certain level has a data, it's going to be larger than or greater than or equal to everything further down from that level. So that means we have moved the root node data, which is 10, which is the largest of all the elements here, to its final position, because if we are to sort this array, 10 should come here. That's the final position of 10. So 10 has moved to its final position. So that means we should not disturb that position furthermore, or should not move or change anything at that index 9. So after this iteration, the accessible portion of the array is only from index 0 to 8. So that's what I mean by accessible portion. Okay. So if you want to keep track of the size, initially the size is all the n elements or the array size elements. So after the first iteration, the accessible size is array size minus 1. Okay. Now we are going to also make the iteration index as part of this. So let me go back to the explanation here. So the accessible portion is going to be from 0 to n minus 1 minus iteration index. So initially, to begin with, iteration index is 0. So accessible portion is from index 0 to n minus 1. So that is if iteration index is 0, the first iteration. Now the second iteration index will be 1. So the accessible portion will be from index 0 to n minus 1 minus 1. So that is n minus 2. That is the last index accessible in the array. So in this case, n is 10, right? The array size is 10. So 10 minus 1 minus 1, so 8. So that is the last accessible index after the first iteration. So basically for second iteration, the last accessible index is 8. And then for the third iteration, it's going to be n minus 1 minus 2, because that will be iteration index 2. So for iteration index 2, which is the third iteration, the last accessible index is going to be 7, and so on. So that's what we're going to do. So now we swap 10 with 3, so 3 comes here. Now you should realize that because of this, the max heap property could have affected, right? So we have to check that whether the max heap property is satisfied. If not, we have to reheapify. So we know how to do that. So compare the data 3 with 8 and 9. The data is less than both the child nodes. We have to swap with the larger. So 9 swap with 3. So 3 comes down, 9 goes here. Now this is not a leaf node position, so we have to compare further down. 3 compared with 5 and 5. 3 is less than both 5 and 5, so we have to swap. Again, you see here the left child gets the preference if there's a tie. So 3 is moved here, 5 goes here. So after the first iteration, this is how the heap is going to look like. So the accessible portion is from index 0 to 8 for this iteration 1, which is iteration index is 1. Now you notice here 9 is now the root, which is the maximum of all the accessible elements. So now we do the same process, swap the data at the root node with the index at the last accessible index, with the data at the last accessible index, so which is 8. So 9 is swapped with 4, 4 now becomes the data of the root, 9 goes here. So once you move 9 here, that's the final position of 9, we should not move it from there. So the accessible portion is only from 0 to 7. So before we continue the next iteration, we have to make sure the max heap property is satisfied, otherwise reheapify to restore it. So here you see 4 is less than both 8 and 5. So swap with the larger of the two, so child node, so 8 comes here, 4 comes here. So again, it's an internal node position, so you have to compare further down. So 4 is less than both 6 and 7, so compare with the swap with the larger. So 7 comes here, 4 comes down here. Now you have to be careful. For this index 3 is not a leaf node position because it has one accessible child node. Actually, there are two child nodes for index 3, but this index 8 is not any more accessible index position. Only 7 is an accessible index position for this iteration. And 4 is the data here, 1 is the data here. 4 is greater than 1. Even though 4 is less than 9, you see this index is not accessible. So we should consider the max heap property to have been satisfied now because 4 is greater than 1. So we should just keep 4 here and let 1 be there. We should not swap anything. Okay, that's a very important thing to understand. So after this iteration, this is now the max heap. So again, 8 is the larger of the remaining data. So as you do this example in paper, you can make sure that every time the maximum data has moved to the root position. So then iteration 2, which is iteration index is 2. So the accessible portion is n minus 1 minus iteration index. So n minus 1 minus 2, which is n minus 3. So array of size 10, n minus 3 is what? N minus 3 is so this is array of size 10, right? So n minus 1 minus 2, so that means n minus 3, 10 minus 3, so this is 7. Okay, so the accessible portion is from index 0 to 7. So swap the root node data with index 7, so 1 comes here as the root data and 8 comes to its final position. So that's its final position, not change it anymore. So then make sure it is satisfying the max heap property. So compare 1 with 7 and 5. 1 is less than both, so swap with the larger child node data. So 1 comes here, again less than both child nodes, so swap with the larger. So now 1 comes here. Now logically this index 4 is a leaf node position because its child node index is not anymore accessible. So 1 comes here, just leave it there. We should not swap it further down. So this is now iteration index 3. So the accessible portion, the last index is n minus 1 minus iteration index, so that is going to be 6. So swap the root node data with the last accessible index, which is index 6. So 5 comes here as the root, 7 comes down. So again reheapify here because 5 is less than 6. So 6 becomes the root data, 5 comes here. You see here 5 is greater than both 4 and 1. So you don't need to swap further down. So 6 is now the root and swap it with the last accessible index now is 5. So 6 comes to index 5, 3 comes here. Again 3 is less than both 5 and 5. There's a tie, so break it in favor of the left index. So 3 comes here, then 3 compared with 4 and 1, 3 is less than 4, so swap 4 and 3, so 3 comes here, 4 comes here. Now 3, this index 3 is a leaf node index for us because its child node index are no longer accessible. So this is the data index 3. It will stay there. So now 5 is the root data, swap with the last accessible index, which is index 4. The data is 1, so 1 becomes the root. Again, 1 is less than both the child node data, so swap with the larger child node, which is data 5. So 5 comes here, 1 comes down here. Again, this is now a leaf node position because this index is no longer accessible. So we leave that 5 there. So then 5 swapped with the last accessible index, which is index 3. So 3 comes here, 5 goes to its final position. Now 3 is less than 4, so swap. So 3 comes here, but this index is now a leaf node because its child nodes are no more accessible. So then we have 4 as the root node data compared with 3 and swap with 1 because this is 2 is the last accessible index. So 1 comes here, and now 0 and 1 are the 2 accessible nodes. So compared with the child node, 3 is larger, so swap it. So 3 becomes the root, and 1 comes here. Again, you don't have to swap further down. Then swap 3 with 1. So 3 comes here, 1 becomes the root. So this is the last iteration because we don't have to go further down. And the last iteration, there's only one element that is accessible, and that is the first element in the array. So by now the array is sorted. Okay. So this is how we go through the reheapify process, starting from the root node. Every time in each iteration, you basically move the data at the root node to the last accessible portion of the array. So when you swap it, so when you move the element from the last accessible index to the root position, you have to reheapify if needed, and that will restore the heap property, and then continue the iterations. So we'll stop here. So next class we'll look at the code, how to do that, this heap sort, and go through one more example, and then we'll continue. Okay, so let me see. So you have 2 minutes, so if you have any questions you can type it out.